Hello and welcome to today's video. In this video, we're going to extend the notion of differentiability to higher order differentiability. So we're going to differentiate the derivative of a function once again and again and again, if that is possible. And in this section, we make this notion of multiple differentials, multiple derivatives more precise. So this section is called higher order differentiability. Now, we'll start with the definition right away, because that is more or less straightforward. As usual, we require an open interval and a function that is defined on that interval and that is differentiable. So let I be a subset of R, and let that be an open interval. And let f be a function defined on the domain I that maps to R, that is differentiable on I. Now please note that we require differentiability on I and not just at a single point in I. And now let's first define what it means for a function to be twice differentiable. And that is the fact simply if the derivative is again differentiable at a given point. Now that derivative, of course, needs to be a function that is again defined on an interval around that point. Otherwise, we cannot take the limit in a reasonable way. And that is why we need f to be differentiable on I, so that f prime is actually a function that is defined in some interval around the point x star. If f was only differentiable at some point x star, we would only have that value and not a function that we can actually work on. So that's why we need f to be differentiable on I and not just at a single point, even though we first define differentiability of f prime, so second order differentiability of f, just for that single point. So let's write down the definition. If the derivative is f prime, and again that is defined on I and maps to R. If that is differentiable at some point x star, then f is called twice differentiable. At the point x star. And of course, the derivative of f prime at that point is then the second derivative of f at x star. So f prime of x star is the second derivative of f at x star. The notation for that second derivative is similar to the one for the first derivative. The most common one is to either just write f double prime at x star, or, and that is convenient, especially if the numbers get higher, f2 of x star, like this. Also, the more traditional notations are possible. You can write that in the way d squared dx squared f of x star. Or of course, the usual variance of this. I just add or variance, basically putting the f here in this place, and of course the x star can also be put into the numerator like that. So these are the variants that I mean. One other notion that is also common is to write a capital D for the differential operator, and then capital D squared, meaning you apply the differential operator twice to the function f, and then evaluate that at x star. So that also means the second derivative of f at x star. As you can imagine, we'll call the function twice differentiable on I, on the interval I on the domain, if it is twice differentiable for every point in this interval. And then this also defines a function on I that will be called the second derivative. So there's the second part of this definition. The function f is called twice differentiable on I, or just twice differentiable, if it is twice differentiable for all points x star in I. And the resulting function that is then usually written as f double prime. That is again a function defined on I, mapping to R, that maps a value x to the value of its second derivative at the point x. That is then called the second derivative once again. Of f, or sometimes it's also called the derivative of order 2 of f. And this is denoted in the same way as above. As a little addition, if f is twice differentiable with continuous second derivative, then f is called twice continuously differentiable. And that is a practically important case, thus it warrants its own name. So if f is twice differentiable with continuous second derivative, then f is called twice continuously differentiable. So this has been the case of a differential of second order, and now it's easy to extend that to arbitrary orders by just turning this into a definition that builds on order k minus 1 and then extends that by 1 to order k. So we can make a similar definition, that is part 2 of the definition for arbitrary order. So for k in n, the function f is called k times differentiable at a point x star in I if f is k minus 1 times differentiable on I So as before, we need differentiability on I, on the whole interval, and the function f to the k minus 1, so the derivative of f of order k minus 1 is differentiable at the point x star. Analogously, f is called k times differentiable on I if it is k times differentiable on every point in I. And once again, if a function is k times differentiable on its whole domain, we often just leave out the domain. We just say the function is k times differentiable, implying that this is meant on the whole domain. So if f is k times differentiable for every point x star in I. And once again, the function that is derived from that, so the function f derivative of order k minus 1, and then differentiate it once again. This is called the kth derivative, or alternatively derivative of order k of the function f, and denote it as, well, usually for arbitrary k you just use this notation here, f to the kth order, or of course you can also use dk dx to the power of k of f, or variants of that one. Or you can also use the differential operator d to the power of k applied to f. And once again, if f is k times differentiable, and in addition to that, the kth derivative is a continuous function on I, then we call f k times continuously differentiable. So if f is k times differentiable, and if in addition to that this kth order derivative of f is continuous on I, then f is called k times continuously differentiable. Third point, for the sake of a more uniform notation, we usually regard the function f itself as its zeroth derivative. So for the sake of a uniform notation, the function f itself is also regarded as its own zeroth derivative. And denoted by, well, f is then derivative of order 0 like this, or d0f. Other notations are rarely used in this case, but this is a usual notation. If you have formulas that involve different derivatives of f and also f itself, then this is often just included as the zeroth derivative. And finally, part 4, a notation for the set of all k times continuously differentiable functions, and you know that one already. We have encountered the set of all continuous functions and also the set of all continuously differentiable functions, and that notation is extended to all k times continuously differentiable functions as well. So the set of all k times continuously differentiable functions on I is denoted as c to the power of k of I. And as a special case, as you know, c to the power of 0 of I simply is the set of all continuous functions on I. And as usual, if I equals R, or if it's clear from the context what we mean, we often leave out this of I. So for I equals R, we also often write c to the power of k and c to the power of 0, respectively. So rather lengthy definition, but on the other hand, that should be fairly easy to execute. You have a function, you differentiate that, and you just differentiate once again, and you get a second order derivative, and you differentiate that, and you get a third order derivative, and so on and so forth. Let's conclude this with a quick example. Now, we'll consider the function f of x equals x to the power of n for powers that are, let's say, at least 2 to keep things interesting. We have already derived the first derivative, f prime of x. That was n times x to the power of n minus 1. And of course, we can just continue to apply that same rule to this function here. And then we get f double prime of x is n times n minus 1 times x to the power of n minus 2. And in the same way, we can get the third order derivative and so on. And this continues up to the point where the exponent has been used up, to say. So this happens at the nth order derivative here. What we get there is, well, we have n times n minus 1. The third order derivative will then add an n minus 2, and so on. So adding all these factors until we finally get to 2 and 1. And then we have x to the power of 0, which is 1. So all in all, this nth order derivative is just n factorial. And that also means the derivative of order n plus 1 is 0, the constant 0. And of course, all further derivatives will also be 0. So if k of x is 0 for k greater or equal to n plus 1. And that also implies that this function is not only differentiable, but also continuously differentiable. All of these functions are obviously continuous, even the constant ones too. So we get continuous differentiability. And formally, we can do this infinitely often, because of course this function here is still differentiable with the differential being 0, as you can see here. So this function is infinitely often continuously differentiable. On R, that means this function is in C infinity. So this is infinitely often continuously differentiable. And of course, this also extends to all polynomials. Every polynomial is also infinitely often continuously differentiable. And at some point, the differentials, the derivatives will just turn into zeros, constant zeros. This also applies then by extension to rational functions. There are usually points where the rational functions are not defined, and so the derivatives might also not be defined at certain points. So these would usually not be differentiable on R, but still you could carry out that process infinitely often, provided you exclude the points where the function and the derivatives are not defined. So basically all the rules that we have seen carry over to this situation. And of course, the next interesting question is, what do we need higher order differentiability for? And what do we need differentiability for at all? And this will be discussed in the following videos. And as usual, I hope I'll see you then.